Very good morning to one and all. I am Ravindran Dey, scientist CI Bhopal. My topic is development of weight sensing system for the fertigation scheduling in soilless grow bag cultivation. Next, please. All you know the soilless cultivation and why this is needed. All these problems. So all these problems they are associated in the soil-based cultivation because we are cultivating the continuously in the soil, and that's why. So my voice is problematic. So that soilless, whenever soil is not favorable, we have to option that soilless cultivation, and soilless cultivation. We can see here different types of the soil cultivation. So we can produce more crop in per unit area and with the less amount of water. So this is the need of these hours. Next, please. So different types of the, next, please. So different types of the soilless cultivation is there, and mostly the crop, fruit crop will grow. But this cocoa beet grow bag cultivation is similar to the soil, but the in soil sensors will doesn't work in the doesn't work in the porous media. So that's why, and also the root volume is limited, and that's why we require the frequent fertigation in the soilless cultivation, and then that's why we consider that the evaporation transpiration is equal to the change in weight, and so change in weight concept is used for the fertigation. Next, please. So this can be used to measure the water loss and also the water gain by applying the fertigation. So for that, we have developed this load cell sensing system in such a way that a single load cell can be utilized to measure the weight loss and weight gain also. So here is, you can see the load cell sensor is placed in the center in such a way that all load is transferred to the single point. Next, please. So for that, we have did that analysis, and we found that so maximum load is transferred in the load cell only, and the minimum is that is base structure, so that is minimum. Next, please. So all stresses is transferred to the single point. Next, please. And then we did the evaluated that weight sensing system by using the known weight, by adding and by unloading. So we found that R square is almost 1, means that sensing system is work well with the controller. Next, please. So this weight sensing system is with the controller, we can control the fertigation scheduling and to deliver the amount of nutrient solution at with the weight changes basis. Next, please. So approach is that weight sensing system give the data to the controller. Controller read that weight loss, and you can see the LCD screen that weight stored and current weight. So comparison between this is automatically done by the controller. And when weight loss is suppose 200 gram is there, we consider 400 because where 4 plant is there. So each plant is 50 ml. We consider that. So we can change also that 100 according to the crop also. So next, please. So this is the flow chart to the weight is already stored, and then current weight will measure, and then difference between there. Suppose that is above the 200 gram, then fertigation is start. Before that, the fertigation tank is filled or not, it check, and then that fertigation start. After that, fertigation is applied, and that weight is measured continuously. And then if that weight is up to the 200 gram is there, then it stop the fertigation. And then after we have given this 1 minute standby time because system requires some stability. And after that, whatever the weight is there, that is automatically replaced with the previous stored one. And then that replaced one is used for the current measurement. Next, please. So this system is evaluated in cucumber and capsicum crop. Next, please. And we have tested with this by measuring the weather data, and we found that one day evapotranspiration, that if that one day evapotranspiration is met by this, our system is not. You can see here 300 that is ml of water required for this means the system is operated for 6 times. For 50 ml of water means 6 times. And then for the different days, it is almost 500 ml, means system is operated for 10 times in a day. Next, please. So for the evaluation, we have recorded the data per unit time, weight data per unit time by using the USD model through the termite software, and then simultaneously we measure this that moisture through the moisture meter. Then next please. Next please. And then we found that so we can found here this moisture measurement is through the meter and through the wet sensing system is approximately same. Next please. So you can see here the fertigation scheduling is done right time. You can see that this is a research work is done in IRI New Delhi in December and January for the same crop we have cultivated there. You can see the 24 is the sunny day that time, and that's why the irrigation is started at earliest at 3 p.m. After that, the next 2, 3, 5 days, it is cloudy nature, means the fog is there. That's why the irrigation is started at even 4 and in one at the night also. Next please. So this is again tested for the cucumber crop for the 4th January 2021, and you can see the here is fertigation start, means sudden spike is there, that is a fertigation start, and 200 weight of water is applied and different dates. Next please. So you can we have concluded that weight develop weight sensing system with the controller was found effective to measure the weight loss in the and gain also in cocoa pit grow bag. Then this system was found efficient to adjusting the fertigation scheduling also, and so this was found capable to apply the right amount of water at right time despite the water labor. Thank you. Next, please. Through this research, we got 2 copyright and 1 patent is applied with this number, and 3 research papers published. Thank you.
Thank you, Dr. Ravind. Anybody is there initially who was not present and they have not been included in the presentation? Those who have come late? No. So it means we have only 2 online presentation left. If online system is okay, then we can take up. Okay? So can we request Dr. Sunil to proceed with his presentation? He is one of the key speaker for the session. Application of IoT in agricultural engineering.
Hello. Hello. Am I audible to all? That I am audible to all.
Yes, sir, you are audible.
So today I will be delivering on application of IoT and in land and water management. Hello.
Yeah, please. आप बोलो वहाँ से.
Hello.
Hello, sir, you are audible. Go with your presentation.
अब बोलो, sir, you are allowed only for, sir, please 8 minutes only. Please restrict your talk to 8 minutes.
The senior delegates and fellow scientists, I am delivering on the application of IoT in land and water management. So myself, Dr. Sunil Karam, working as Associate Professor at Center of Excellence on Digital Technologies for Smart and Precision Agriculture of Mahatma Phule Krishi Vidyapith, Rahuri. So I will be delivering on the basically on IoT applications and initiatives of Mahatma Phule Krishi Vidyapith has taken to develop the IoT-enabled different irrigation water management systems. And today, nowadays, digital agriculture, smart agriculture, precision agriculture, climate smart agriculture, village, these words are become as a buzzwords for the application of digital technologies or IoT technologies in the agriculture. So if we see the digital agriculture is the the transformation of agriculture from traditional agriculture practices to the semi-autonomous to autonomous agriculture practices, and these can be achieved through the application of IoT technologies in the agriculture sector to achieve the benefits like increased productivity, resource efficiency, and sustainability in the agriculture. So I tried to show some components of the digital technologies in agriculture, precision agriculture, and climate smart agriculture, like IoT is one of the applications, then mobile and web application, drones, remote sensing, GIS, artificial intelligence, robotics, and the one of the most important component of the IoT enabled any kind of the system is the different types of the sensors. If you talk about the precision agriculture, we need to address the spatial variability, then spatial and temporal variability of the plant, then soil and weather conditions, along with the applications like the irrigation systems. And this goes through the principles of 4R, that is right selection of the right source, selection, application at the right rate, right place, and the right time. This could be achieved through only the IoT-enabled sensor-based systems, which could be developed for the increase in the productivity and production of the agriculture produce. Then these are the few core technologies which are available, that is IoT, which connect devices for real-time monitoring, then data analytics, that is convert sensor data into the actionable insight, and the last most important is the automation, that systems that react automatically to the sensor readings, like the, for example, the irrigation control systems. So there are, then again one more term is smart agriculture. So smart agriculture, again it has a few components like sensors. We can monitor the soil, water, light, humidity, temperature management sensors. Then softwares like specialized software solutions that target specific farm type for applications, that is called as IoT platforms. Then connectivity, that may be cellular connectivity like 3G, 4G, 5G, or the LoRa connectivity, Bluetooth connectivity, or the Wi-Fi connectivity. Then if we want to real-time and location-specific advisories as far as the weather conditions or the irrigation water management is concerned, we need the GPS or the satellite locations. Then robotics, that is autonomous tractors, processing facilities, data analytics, that is done to the standalone analytic solutions, data pipelines for the downstreaming solutions. So this how we could do the smart agriculture by following the six steps in the cyclic manner. These are the components of the smart agriculture. Then we turn on to the main topic, that is the IoT applications in the land and water management. Specifically, I will focus on the applications which are developed by the Mahatma Phule Krishi Vidyalaya for the irrigation water management and the other applications in the agriculture. So IoT is simply a network for interconnected things or the devices which are embedded with sensors, softwares, networks, connectivity and necessary electronics circuitries which can communicate with the sensor and the controller and the other system via the data communication systems and do the works autonomously. So these are the key components of the any IoT enabled systems which has the particular applications in the agriculture. The most important and key component is sensors, which measures the environmental crop conditions, for example soil moisture sensors or the weather conditions, that is temperature, humidity and other things. Then next component is the actuators. We need the hardware device to communicate between the application part and the software part. Those are called as actuators or the controllers. Those devices that takes action based on the sensor data, like irrigation on and off of the irrigation pumps. Then the connectivity is another key component that are the different types of the networks like Wi-Fi, LoRa, GP, 5G for the communication within the software and the controller and the end user. Then data analytics and the data storage is the another challenge in the IoT enabled system applications in agriculture, which can be done through the cloud or the cloud edge computing systems. So these are the few initiatives and important innovative works that are done at the MPKV Raupuri as far as the IoT enabled systems are concerned. So IoT enabled location specific real-time irrigation scheduling systems for the single crop, we call it as auto PIS. Then IoT enabled location specific real-time irrigation scheduling system for multiple crops, that is smart PIS. If we have more than one crops, we can use this kind of the system. Then IoT enabled automatic weather stations we have developed in-house. We have developed the soil moisture sensors based on the different principles, that is capacitance, FDR, principle, then resistance principle, and we found that the combination of the principle, that is FDR and capacitance, those sensors work more efficiently than the other two, and these we have developed the end-to-end solution of the IoT-enabled soil moisture irrigation settling system based on the soil moisture sensors. So these are the few initiatives as far as IoT applications are concerned in irrigation water management. All we know that the irrigation scheduling, we need to answer the three questions, that is how, when, and how much, by addressing the spatial and temporal of the soil, weather, crop, and the irrigation system needs. So these IoT-enabled real-time precision irrigation water management systems are specifically divided into the two categories, that is weather-based systems and soil moisture-based systems. Weather systems means the use of the weather parameters to find out the water requirement, particular real-time water requirement of the plants and crop, and soil moisture-based is based on the soil moisture or the depletion criteria. So first we try to develop the mobile application for the estimation of the reference crop evapotranspiration, which is the major parameter for the estimation of crop water requirement, and we have developed the mobile web-based application as well as the desktop-based application.
Sir, please come to conclusion.
Yeah, just then another system we have developed the web-based real-time irrigation settling system based on the crop, soil, and irrigation data. I am going hurriedly. Then we have developed the auto full irrigation settling system, that is auto PIS, which is the end-to-end solution that farmer needs only the mobile application in his mobile smartphone device, and he can operate his pump from the remote areas. He can on and off the pumps. So this has the four components measure, that is the crop, soil, and weather and irrigation system, then the controller, then the water meters. So these systems work on two principles, that is the time-based systems and the volumetric-based systems. Then these are the few side features of the auto PIS. The video is there, I will skip that video. Then another is the smart full irrigation settling system. Why we call it as a smart? Auto PI is for the single crop system, but the farmers are a number of crops, more than 2 crops, 3 crops, or 4 crops. So we have developed this kind of the system which accounts the 10 crops, or we may call it as a 10 crops can be irrigated through this irrigation settling system simultaneously by using the IoT enabled irrigation management system based on the weather data. These are the silent features of the IoT enabled location specific real-time irrigation settling system, that is for the multiple crops. This is the video, I'll skip this video. We installed these systems on the farmers' fields also, and we get good feedback, and we are on the verge of commercialization of this type all these systems. Then another, we developed the sensor-based systems. In this also we consider integrated the soil moisture sensors with the cropping systems, that is farm, crop, soil, irrigation systems, and we have developed the irrigation settling system based on the soil moisture content in the soil. So we have developed the different types of the sensors, as I told earlier, that is capacitance based, resistance based, and then FDR capacitance based. So these are the different types of the sensors. These are available in the single depth or multiple depth systems. So this is the evaluation of the soil moisture based irrigation settling system in the research farm of the MPKV Rahuri. These are the silent features. Then I will skip this video. Then we have developed the other IoT enabled systems like full smart weather systems. So we have developed the 6 types of the weather systems starting based on the weather parameter measurements. So it measures temperature, humidity, rainfall, wind direction, wind speed, and all the parameters which are required for the settling of the irrigation. So these are the components of the developed irrigations, that is automatic weather station. Then we have developed the IoT enabled AWS star topology system. So we need to measure the variability in the rainfall at the different locations. As on today, we are using the average rainfall, but if we have the such type of the systems, we can measure the variability within the watershed or within the command area or within the at the block level, and we can have an average value for that region. So we have developed the dashboard also. Then we have developed certain low-cost IoT-enabled temperature devices which cost from the 2,500 to 5,000 rupees, which could be portable also, which can install in the protected cultivation inside the poly house, shed net house, or outside the in the open environment. So all these are which can be that can Wi-Fi, uh, develop the such type of the dashboard also. Then we have developed the IoT-enabled panning operation system by using the load cell principle as well as the ultrasonic pressure sensor systems, and we found this the accuracy of this within the plus or minus 5%. So these are the few devices. Again, trench water level recorder. Then we have developed also automatic siphon system for the pond irrigation. Then we have developed fertigation irrigation scheduler system, which is IoT enabled again. Then IoT enabled tensiometer to measure the soil moisture content. So we have developed the 48 plus mobile and web applications, and we have received the copyright for all these systems. So just 1 minute, sir. So these are the different units. We have developed the IoT enabled. Yes, sir. Thank you. Yeah, thank you very much, sir.
And all the dignitaries. I am presenting here the research on topic machine learning based reference vapor transpiration prediction for districts of Madhya Pradesh. As you know the background, I am directly moving that our meteorological data collections is very limited, and in data scarce region the development of reliable model that can predict the ET0 accurately with minimum climatic input is needed for making irrigation decisions. So we know that there are different approaches for irrigation scheduling, but farmers need cost-effective, sophisticated, easy-to-use technique and solutions so that we can implement that in large number of cultivated field. So here we have tried three different machine learning models: random forest, support vector regression, and ANN to predict the ET0 with minimum climatic input. So these are the three different machine learning models we have did, and the study there is the different districts of Madhya Pradesh. So there are 11 agroclimatic zones in the Madhya Pradesh, and these three machine learning models were tested and trained for all these 11 agroclimatic zones of the Madhya Pradesh. So this is the methodology of predictions of reference vapor transpirations, in which we collected the meteorological data and then we estimate the ET0 using Penman-Montague method, and different weather parameter input scenarios we have developed, and then finally we data partitioned into training. 80% data was used for the training, 20% was used for the testing, and finally we did the ET0 predictions. And this result of machine learning model was validated using FAO Penman-Montague method. So we use this daily meteorological data of period 2003-2022, and this whole analysis was basically done using the Python, using the Jupyter notebook. So this is the descriptive statistics of weather data set, and FA56 PM ET0. The correlation was developed between the different weather variables, and the highest correlation with the ET0 was found with the maximum temperature of 0.91. So these are the 6 different machine learning models with different input combinations was prepared and tested. The model performance indicators like coefficient of determination, root mean square error, and mean absolute error were used to validate the performance of the model. And we found that the random forest model having highest prediction efficiency as compared to the support vector regression and the ANN model. And we can see that the S3M1, which is the combination maximum temperature, minimum temperature, and the wind speed, giving the highest R-square and the minimum RMSE and mean absolute error. So these are the plot between ML based predicted and ET0, FA56 ET0. So already I said that this random forest algorithm predicted the ET0 with highest R-square of 0.95 and lowest RMSE of 0.56. So we deploy this ML model using the Flask to prepare its HTML web-based application, and we use the model.pickle file of ML model, and then we integrated using the HTML code, and using application programming interface API, the meteorological data is fetched and linked with the best ML model random forest to forecast ET0. So this is the web display of predicted ET0 using ML model. So we have to input our place, and for that place we have to give different input combinations, and based on that it will predict the reference evapotranspiration. So we validate the result in the field. So field experiment was carried out using the sprinkler irrigation for wheat crop, deep irrigation for okra crop, and deep irrigation plus mulching for okra crop. So three different levels, 10% MAD, 30% MAD and 50% MAD used for sprinkler irrigations, and 10, 20, 40% for drip irrigation with mulching and without mulching. So different crop growth parameters were measured in the field, and we finally compared that the predicted ET0 by that random forest model were used for irrigation scheduling of wheat and okra crop, and we compare the ET0 estimated by that random forest model with the FA56 method and pan evaporation method, and very good matching between the in the reference evapotranspiration predicted by random forest model and pan evaporation and the FA56 method was found. So findings are the random forest model outperformed the SUAR and ANN model for ET0 estimations, and validation using field experiment revealed that the machine learning algorithm can be applied successfully for prediction of the crop water demand and further for scheduling irrigation. Thank you.
Thank you. Thank you, sir.
I hope my screen is visible. Good afternoon to all. Myself, Dr. Vibhav Malanskar, working as Research Associate in Center of Excellence on Digital Technologies for Smart and Precision Agriculture at MP Rauri. The topic of my presentation is the development of real-time infiltration rate measurement using IoT-enabled automatic double-ring infiltrometers. So as we know, the soil infiltration is a very important process by which water enters into the soil by the force of gravity and surface tension. So this understanding this phenomena, this soil infiltration, is very important to us to plan the different structures in watershed, as well as to design the efficient irrigation management systems and to access the soil moisture. So the importance of soil measuring infiltration rate, as we know, the traditional method, we have to go to the field, install the two rings, that is one inside, one outside, and we have to wait for 6 to 7 hours to get the soil infiltration rate. To overcome this manual intervention, and to get the accuracy in measurement of soil infiltration rate, we have developed two concepts. That is automatic ring infiltrometer, which is based on the phenomena like recording type rain gauge, where one flute is there, and rotating drum and pin arrangement has been given. We have specially designed one chart, which is an infiltration chart. Whatever infiltration readings measured by the infiltrometer will get the reading on the chart. And the second one we have developed, that is IoT enabled double ring infiltrometer. Here we have used ultrasonic sensor to measure the real time water level depleting in the soil. So first one is automatic ring infiltrometer. These are the different components, that is metal infiltrometer ring, the standard infiltration rings, that is inner ring having 30 centimeter diameter, outer ring having 45 centimeter diameter, and both the rings having 40 centimeter height we have developed these type of things in the metal. Then float sensor, we have two types of float sensor, inside the ring and outside the ring, to get the automatic water to flow the water automatically inside and outside the ring. Then we have specially designed one float and pane assembly for this purpose. Then microcontroller and timer to get the results. Then two DC pumps, one is for inside ring and one is for outside ring. And one 200-liter tank with stand has been taken for this experiment. These are the different components we have used for the development of this infiltrometer. This is actual automatic ring infiltrometer. Here we can see in the picture that is tank having 100-liter capacity which is filled with water. The two 12-volt DC pumps are given for filling the water inside and outside ring. Then float and pane assembly to inside that assembly chart is there, infiltration chart having 10 centimeter measurements, and which will record the continuously whatever infiltration rate is recorded by the system. So the experimentals in the field, filtration, here we can see that observation was started at 10 a.m. and at 16 hours, and the total infiltration rate we can measure easily, that is 45 to 46 centimeter. Then we have compared this developed infiltrometer with the conventional infiltrometer, and we get the very accurate and good results in automatic ring infiltrometer. These are the silent features of this system. Now the next system we have developed, that is automatic IoT enabled automatic infiltrometer, which is sensor based. This system is already similar to the earlier system. Here we have replaced the float and pane assembly with the ultrasonic sensor assembly. So ultrasonic sensor having capacity of 200 centimeter, and which measures the real-time water level inside the ring. So whatever data recorded by the ultrasonic sensor, which will be fetched by the open source web platform, that is ThinkSpeak, where we can get the minute-to-minute reading of the infiltration rate along with the graphical representation.
Sir, please conclude your conclusion.
Yes, sir. These are the traditional infiltration rate. These are the silent features, as the assembly infiltration rate which measures continuously. Then there are it overcomes the difficulty and limitations which encountered while using the conventional infiltrometer. Also, it reduces the heat. In conclusion, the IoT enabled infiltrometers, that is automatic and IoT enabled, which are aligned with the future of agriculture, where data-driven decisions can play an important role. And these are the low-cost technology we can use in the experimental purpose for researcher as well as the scientists which are involved in the irrigation water management. These are the QR codes where you can download the flyers of these two developments.
Thank you.
Thank you, sir.
Thank you. Now we have come to the conclusion of our this important session, and we are fortunate enough to have among us Dr. Suresh A. Kulkarni. So he has a vast experience, and if sir, I request you to highlight the things in 5 to 6 minutes, please. So what is your experience you can share with us? So that will be great.
Hello, check.
So, first of all, thank you very much, Mr. Chairman, for this opportunity. I am really not scheduled, but I was really asked by the authorities here to give a keynote. But anyway, I would like to just share because I have worked in the irrigation field for last 45 years, and I am really extremely happy that I was a student of this college, and after 57 years, I am in this room where we have to have a botany, if I remember correctly, botany laboratory. So that is another my nostalgic kind of a thing. So once there are a lot of things, but very quickly, which I want to share with you. There are some learned, Dr. Gore sir is there, Vice Chancellor and reputed from Kharagpur sirs are there, Professor. So I thought that is a good opportunity. Please take it forward. Next, please. Next year, copy karo naka. Next year. I will not go, you know this, because irrigation and agriculture water management, basically all over the world, it is all agriculture water management. And irrigation management is a part of agriculture water. Pure rain-fed agriculture or pure irrigated agriculture. It is always a mix. In some places, of course, there is a pure irrigated agriculture. Next. I want to just show here, I will not take much time, just show the country's availability that we have, 4,000, but 50% of the water you have get evaporated. And we have only 1,990 renewable water. And out of this utilizable water, because of the, you can say topography, technology, we can use only 100 billion cubic meter of water. Only that means renewable 43% can be, 53% can be used. And going further, we can see how much we are using for irrigation. 310 billion cubic meter of water, it is estimated. There is no proper estimate in our country. And as regards the groundwater, we are the largest groundwater user in the world, 210. British much nearly about irrigation water in the world. So here I will not show you everything. Here only to show many, you must have seen this picture. We need to understand what is scarcity. Scarcity or water stress, it is called a water stress. When water demand exceeds the water supply, then it is called as water stress. In many African countries, there is no demand. Even if they have physically less water, they don't have stress. So in India, a lot of activities, population increase, industrialization, urbanization are happening. So more and more demand, less and less water availability. So there is a water stress. India is a highly water stress country according to this. We are going to be in 2030, 80% area of the country will be water stress, highly water stress, not extremely water stress. And for this irrigation, unless and until you manage the water in irrigation better, you will not be able to solve the problem of water problem of this country. Next. Irrigation, I will not take much time. Irrigation is changing. It is not just simple application of water. Now we are IoT, there are different purposes. And now scientists are saying, last one, sustainable irrigation. Sustainable irrigation means it is socially, equitably, environmentally, technical, institutional, hydrological, productivity factors. And most important, we want to release water from irrigation sector to other sectors. That is which is a big challenge. And this is what we want to do in India also. How to release water from irrigation sector to other sector. That is what is sustainable irrigation. Next. So you can see the country's irrigation from 1910, before independence, only how much area was there? Only 14 million hectares. Now we are the biggest irrigated area in the world. That is 78 million hectares. That was the biggest area we have in this. But if you see this groundwater, just take it, just here, I will back take. So groundwater issue, grey by issue, canal irrigation is almost stagnant. Canal irrigation from last 30 decades, despite of so much of investment in irrigation, dams, so many things we are doing, but the canal irrigation is almost stagnant. Groundwater irrigation is increasing. So that is a matter of concern really. Why canal irrigation is not increasing? There is something wrong, So this is what I want to show here. Next. So you can see for India, irrigated crop water stress by country. This China, but the stress is not that high. We are equal, China also almost irrigate 76 million hectares of water, but they use 50% water than what we are using for irrigation. Okay, so you can see this China is managing much better this irrigation sector. So you can see the stress. India will be facing a lot of stress for that crop. Crop yield will be already low, and in future they are going to be low because of the water shortage. Next, please. So these are the two water intensive crop in India. almost the rice and sugarcane crops use more than 60% of the country's irrigation water, accounting for just 24% of the cultivated area. So how to reduce this guzzling crop? Maharashtra, almost 70% of the water goes for irrigation. Although Maharashtra water stress state. So these are the challenges for the irrigation engineers. Next. And now irrigation efficiency, this is a big word used everywhere. There are a lot of misunderstandings in irrigation efficiency, taking water from reservoir to field. We have different conveyance efficiency, distribution efficiency, and field application efficiency. So I will not take much time here, but there is a lot of misunderstanding about this concept. Next please. There are some misconceptions and misunderstandings of irrigation terminology. Time for reflection of all over the world. Now we have heard about the FAO, we have modified Penman method and so many things. Now scientists are questioning that really. So what is crop water irrigation requirement? While calculating the ETO, the ETC from meteorological data is used. ETC, which is in fact